Okay, we're going to take a look at a hypothesis testing. Specifically, we're going to look at the p-value approach to hypothesis testing. Start with a research question, and then we'll formulate hypotheses. In this case, our question is the average, or population mean, number of customers in line greater than 6? Notice that our question concerned a population parameter, in this case the population mean. Then we've got a standard deviation and a random sample. But the hypotheses, our research hypothesis, mu greater than 6, that comes directly from the research question. Is the average, or the population mean, greater than 6? Transfer that right to your research hypothesis. And the null hypothesis is the complement to that with an equal sign. You could put either mu equal to 6, as I have here, and that really is the specific hypothesis you're testing. You could also put mu less than or equal to 6, because if you do in fact reject HO and conclude it's mu greater than 6, it's also going to take care of hypotheses like mu equal to 5, because if it's greater than 6, it's going to be greater than 5 as well. Now we'll just use the central limit theorem and those ideas, and we'll calculate the mean and the standard error for the sampling distribution. Now we'll formulate a decision rule. So we're going to start with that null hypothesis, and then we're going to compute the probability of obtaining the statistic that we obtained under the assumption that the hypothesized value, that the one in the null hypothesis, is true. That probability is the p-value. If it's low, then we're going to reject the null hypothesis. Alternatively, if the p-value is high, we will not reject the null hypothesis. We'll consider the null hypothesis to be plausible. And we want to when it's low enough to warrant rejecting the null hypothesis. Well, that depends on the problem's context. And one of the major advantages, as opposed to the critical value approach we'll talk about in another slide, we do not rely solely on some kind of etched-in-stone cutoff. Okay, we're going to apply those cutoffs here anyway, mainly as a matter of convenience and from a learning standpoint. So we're going to look at p-values as being low enough if they're either lower than 0.05 or 0.01, and we'll give you those levels of significance, or alpha levels, we'll call them later, 0.05 or 0.01. Those will be given with the problems in here. Outside of here, you have to make your own decision about whether or not you would prefer 0.05 or 0.01. Here's our sampling distribution. We hypothesized 6, and our sample we got 7.2. So we want to know how likely it is we would get that sample mean of 7.2 if the real population mean were 6. And some of the times when the population mean is 6, and rarely you're going to get exactly 6. You might get 6.1, 5.3, in this case 7.2. Well, sometimes you're going to get a mean that's different than 6 just because of random error. And sometimes you're going to get a mean that's different than 6 because the population mean really isn't 6. So we got 7.2. So we want to know if it's reasonable to think that it could have come from a population with mean 6, or if it's so far away that we cast doubt on that null hypothesis, or that hypothesized mean of 6. So we've collected that data. We got an average in the sample of 7.2. Then we'll compute the test statistic. This is just like the formula we had for sampling distributions, except for now we have z-test. We still have the sample mean minus. Now we're subtracting from a hypothesized mean. And so that's over the standard error. And we compute this all out. And the sample mean that we have is 3 standard errors away from the hypothesized mean. So now we're going to compute the p-value, the probability of observing a statistic this extreme, this or more extreme, when the null hypothesis is true. So here again, our null hypothesis is 6, our sample mean is 7.2, and so our p-value is going to be the area out in that tail. So we know that's 3 standard errors above, that 7.2 is 3 standard errors above 6. We can use the z-table to find that area to be 0.4987, and that leaves 0.0013 in the tail. Again, that's a fairly low likelihood. Therefore, we're going to reject HO because it's almost never going to happen. That is, we're almost never going to get a sample mean of 7.2 if the population mean is 6. Again, that 6 comes from the null hypothesis. Therefore, we can be confident that the population mean number of customers in line exceeds 6. Let's think about what to do about that. Mainly, we need to take some action to reduce the length of time or the number of customers in line, which would of course reduce the length of time that a customer has to wait in line. We can do that by hiring additional checkers, by installing more efficient scanners, or by adding some self-checkout stations. Some of the advantages of the p-value approach. Even though we're using cutoffs in here, you don't have to. You can report specifically the probability of obtaining a particular statistic under the assumption that the null hypothesis is true. People can interpret those probabilities using whatever decision criteria they want to. You'll see when compared to the critical value approach, in the critical value approach we had a p-value of 0.051, we would fail to reject HO. We wouldn't note the fact that that's really close to what our cutoff is. So reporting the p-value gives us not just a reject or a fail to reject, but an exact probability that we can then make sense of on our own. Similarly, if we got 0.049, this time we would reject HO. The difference between 0.049 and 0.051 isn't really that much, but yet, using a critical value approach, we make completely different decisions. The p-value approach, we can look at exactly that probability. Another advantage is that you can compute p-values for a wide variety of statistical tests. Everything we'll do in this course and everything you could do in many other courses. Anyway, you can get these p-values and they're going to have the same basic meaning for all of those tests. That is, when the p-value is small, you can reject the null hypothesis because if the null hypotheses are true, it would be unlikely to get the statistics. Again, if you just report reject or fail to reject and don't give a p-value, then whoever's reading the report is stuck with your conclusion, and they might be willing to accept more or less error than you.